This is tutorial number 4 of electrical engineering and power control. So this is about transformers. There will be a lab session on transformers. Therefore, this tutorial will help that lab session as well. The transformer exact equivalent circuit. So as you can see, there are two windings, primary winding and the secondary winding. Primary winding is at your left and secondary winding is right. So RP JXP, that is the primary resistance and the reactance, RS and XS, that is secondary resistance and reactance. Okay. So RC and XM, they will represent the core losses of the transformer. So as you can see in here, the input voltage is VP, or the primary voltage, and the input current is IP, and the output voltage is Vs, and the output current is Is. So this transformer equivalent circuit, this is made considering the losses of the transformer. You can see in previous model, there is no electrical connection between primary side and secondary side. In order to make that connection, actually this is just a model, right? This is not the actual way, but in order to represent both primary and secondary in a single circuit, we are using this. So as you can see in here, all the other quantities will not change, right? But can you see that equivalent resistance Req and Xeq has changed? Req, it is Rp plus A squared Rs. Xeq is equal to Xp plus A squared Xs. That is because this is the approximate transformer model referred to the primary side. And can you see the current, secondary current, or the output, not the secondary current, the output current, that is Is divided by A, and the output voltage is A into Vs. A is the turns ratio, as you all know, which is Np divided by Ns. So in this figure we can see both input, or the primary and the secondary parameters in a single diagram. Then this is the approximate transform model referred to the secondary side. In here, what we are doing is we will convert our primary side from primary side to the secondary side. So when we are doing that, in here Req is changed as Rp over A squared plus Rs. Then Xeq has changed as Xp divided by A squared plus Xs. So A is the turns ratio again. And so the primary quantities are Rc and Xm. They have changed to Rc divided by A squared, and Xm has changed as Xm divided by A squared. So in here, the input voltage, it is Vp divided by A, and input current is A into Ip. So this is open circuit test. In open circuit test, what we are doing is we will disconnect the load or open circuit the output. So when we open circuit the output, there won't be any current flowing through the load. That means, according to our figure, ISOA is equal to 0. When ISOA is equal to 0, there won't be any voltage drop through Req and Xeq. Therefore, the total current will flow through only the excitation branch, which consists of RC and XM. Therefore, using open circuit results, we can determine RC and XM values. So as you can see, when we are disconnecting the load, open circuit voltage means that is actually the input voltage, because there won't be any voltage drop through Req and XEQ. Okay, and therefore using this open circuit test we can determine RC and XM. Circuit test is the other test that we are performing on a transformer. In here what we are doing is we will short circuit the secondary side, or the load is short circuited, then we are measuring, then we are keep on changing our input voltage. So input voltage is given as BSC, short circuit voltage. So in here what is happening is since the load is short circuited, most of the uh, most of the current will flow through REQ and XEQ, because compared to so if we refer RC and XM values, they are quite high. So uh, therefore we are short circuiting the output as well. Because of that, there will be very small amount of current going through RC and XM. Uh, Therefore, we can assume that the current going through RC and XM, which is the excitation branch, is very small. So the total current will go through REQ and XEQ, right? So therefore, using short circuit test, we can determine REQ and XEQ. This is another uh, representation of the transformer, right? If we want to represent all the primary voltage, primary resistance, reactance, and secondary resistance and secondary reactances all together, we will use this model. So, so it is our duty, or in the question also you will be given whether which model that you have to prefer. So here also we can see that everything is presented as shown previously, but note down the position of the excitation branch, which consists of RC and XM. So this is another representation. That means the previous representation referred to the secondary side. So you can compare our previous representation with this one. Okay, so consider question number 1 for today's tutorial. The secondary winding of a transformer has a terminal voltage of VST to 182.8 sin 370 t volts. The turns ratio of the transformer is 100 to 200. That means NP is equal to 100, NS is equal to 200. Therefore, A is equal to half, or 0.5. If the secondary current of the transformer is IST, so secondary current is given as 7.07 sin 377 t minus 36.87 amperes. What is the primary current of this transformer? So then you are asked to find what are its voltage regulation and efficiency. The impedance of the transformer referred to the primary side REQ is given, XEQ is given, RC is given, XM is given. So therefore, we have to choose the model that we have learned previously, which consists of uh, REQ and XEQ, and which is referred to the primary side. Okay, so like this. So since no particular equivalent circuit was specified, we are using the approximate equivalent circuit referred to the primary side. Okay, so in here you can see this is the previous model that we have learned. VP is the input voltage to the primary voltage, IP is the primary current, VSC is the secondary current, ISC secondary voltage, ISC is the secondary current. REQ and XEQ, they are referred to the primary side, and those values are given below. Then RC and XM value are also marked in the figure. So first of all, we can find, since the secondary voltage and current is given, Vs we can find at 282.8, that is the peak value. So if we divide it by root 2, we can find the RMS value, which is 200, and therefore we will make Vs is equal to 200 angle 0. We will make Vs as our reference. So compared to that one, Is also given 7.07 divided by root 2, and it is and the angle is also given minus 36.87. Therefore again 7.07 is the peak value. When we divide it by root 2, it is 5, and the angle remains same, minus 36.87. Okay, so then we are going to find what is AVS, right? AVS is equal to 100 0, because A is equal to 0.5. Can you remember? A is equal to 0.5. 0.5 multiplied by 200 angle 0, that is 100 volts. Then the secondary current referred to the primary side, we can find Is divided by A. So A is equal to 0.5. So 5 divided by 0.5, it is 10, and the angle remains same as minus 36.87. Okay. Then if you apply Kirchhoff's voltage law to the given previous circuit, Vp, that will be equal to AVS plus Is over A multiplied by Req plus JXEQ. Okay, so Vs dash and Is dash refer to, Vs dash is actually AVS, Is dash is Is over A. So therefore 100 angle 0 plus 10 angle minus 36.87 multiplied by Req is 0.2 plus JXQ is J 0.75 ohms, right? So therefore it will give you 106.2 angle 2.6 volts as the voltage. Okay. It's an excitation branch. In the excitation branch, there will be two parts. So one will be the current through RC, and the other one the current through XM. So current through RC we can mark it as IC. Current through XM we can mark it as IM. So therefore, as you can see in the figure, the voltage through both components are equal to VP. VP is 106.2 angle 2.6. So therefore we can find IC by 106.2 angle 2.6 divided by 300. 300 is RC value. Then we can find current through XM, Vp divided by JXM value. Vp is 106.2 angle 2.6. JXM value, it is J80. So it is already given. So by substituting it here, you can find IA. Then when we add them together, we can find the total current through the excitation branch, IEX, right? So after we add them together, what you will get is 1.37 angle minus 72.5. Okay, so if we apply Kirchhoff's current law to the previous figure, IP is equal to actually Is over A plus IEX. That means Is over A, which is the current going to the output, plus the current going to the excitation branch. So we have found Is dash, which is equal to Is over A previously. Then IEX also we have found the current to the excitation branch. Therefore IP is equal to 11.1 angle minus 41.0 amperes, right? So like this we can find IP value, which is the primary current. Then you are asked to find the voltage regulation of the transformer at this load. Okay, so before going into the equation, So we'll see what is the voltage regulation is, right? So voltage regulation is calculated, right? Is calculated like this. So when we have a load, right? When we have a load, um, it is calculated like this, right? It is calculated as a percentage, right? So it is actually no load voltage minus full load voltage divided by full load voltage, right? So what is meant by no load voltage? No load voltage means when there is no load, when the output is open circuited, according to our figure, right? According to our figure, there won't be IS over A. IS over A will be 0. Therefore, uh, when the voltage at no load will be equal to VP. VP is the primary voltage. So you can refer the diagram for the diagram. When we disconnect the load, there won't be current through the load. When there's no current through the load, output voltage will be equal to VP. So VP is our no load voltage, right? Then full load minus full load voltage. Full load voltage is when there's a load. So when we have a load, the voltage it is also given there. It will be AVS, right? Turns ratio into VS, secondary voltage, right? Divided by full load voltage, which is again AVS. So when we are substituting the values for voltage regulation, we will only substitute the magnitudes. So we will omit the angles, right? So VP is 106.2, right? AVS is 100. So therefore, after we substituting it in here, our voltage regulation is 6.2%. Then when we have our input voltage and input current with the angle, we can find the input input active power, which is equal to VP into IP cos theta. So remember, VP and IP, these are RMS values. So VP is 106.2, IP is 11.1, then the angle theta is 2.6. So therefore, finally you are getting input power as 854 watts. Okay. Then um, the output power, right? Output power that will be equal to Vs into Is into cos theta. Since we know output voltage and output current, we can calculate output power. So Vs is the RMS output voltage. It is Vs, right? So 200. Is is 5 and the angle between them is 36.87. Therefore multiplied by cos 36.87, it will be 800 watts. Therefore the transformer efficiency we can calculate neta output power divided by input power multiplied by 100%, which is equal to 93.7%. So question number 2, it is 20 kVA 1000 to 480 volts distribution transformer, right? So here 20 kVA, right? That is the rated power of this transformer, right? Rated power, rated apparent power, right? So here 8480, that is given for us in order to calculate the turns ratio. So 8000 divided by 480, you can get the turns ratio A, right? Then RB, RS, XP, XS, RC, XM, those values are given. Each and every value are given to you. Right? So here also you can see that compared to RP, RS and RP and RS values, RC value is very high. It is in kilo ohms, 250 kilo ohms. When compared to XP and XS, XM value is very high. It is in also kilo ohm range. Okay. So let's go to the question. The excitation branch impedance are given referred to the high voltage side of the transformer, right? So here high voltage side in here is actually it is the primary side. So here, so if you refer the first line, in the first line you can see 8000 to 480 volts. 8000 is referred to the primary side, 480 is referred to the secondary side. Therefore, high voltage side means the primary side. Okay. So the question A, find the equivalent circuit of this transformer referred to the high voltage side. So in here, what you are asking to do is finding the equivalent circuit referred to the primary side. High voltage side means the primary side. Then assume that this transformer is supplying rated load at 480 volts and 0 0.8 power factor lagging. What is the transformer input voltage? Right. So you were given the load parameters. Right. Then you were asked to find transformer input voltage. Right. Then uh, what is its voltage regulation? Then you are asked to find the voltage regulation. Then what is the transformer efficiency under the conditions of part B? Okay. So again, as I have told you, A can be found as 8000 divided by 480, which is equal to 16.67. Since if you can remember our previous model, so since you were given RP, XP, RS and XS, and all the values you were given, therefore we have to refer to this model, not the REQ XEQ model. Okay, so 32, so refer the equivalent circuit. 32 ohms is the value of RP, J45 is JXP value, then 250 kilo ohms, that is RC value, J30 kilo ohms, that is the XM value, right? So 13.9 ohms. 13.9 ohms is, if you can remember, when we are taking the components from secondary side to primary side, it should be multiplied by A squared. So A is 16.67 squared, A is 16.67, A is 16.67 squared into RS, which is 0.05 ohms. We are getting this 13.9 ohms. Then A squared into XS, which is equal to 16.67 squared multiplied by 0.06 ohms, which is equal to J 16.7 ohms. Then again consider the current. It is IS over A and voltage is AVS. So we have found the equivalent circuit. What the only things that we don't know yet is uh, the currents and voltages. Uh, so so this is again the previous diagram, right? So by seeing this, okay, by seeing this, if you can remember, we were given the load conditions, right? So load is connected to the secondary side. So when we have our secondary, we will see at the output current IS, right? Current. So remember, at the secondary, in the actual transformer, what we will see is at the output is current IS and voltage VS. So uh, you were given you were given uh, you were given the load conditions in part B. So it is said load is 480 volts, right? That means output voltage is 480 volts. VSC is 480 volts, angle 0, right? Then it is 0.8, power factor is 0.8 lagging, right? So if we have found cos inverse 0.8, that is equal to minus 36.87 angle. Since it so if you can remember, at first I have shown you that at this transformer the output or the rated conditions is 20 kVA. 20 kVA means that is the Vs apparent power, which is Vs multiplied by Is, right? Vs multiplied by Is. 20 kVA is Vs multiplied by Is. So if I divide 20 kVA with the Vs value, which is 480 volts, I am getting the magnitude of the current as 41.67. Is I am getting as 41.67, and it is told that it is lagging 36.87 degrees. Therefore, the angle of Is is minus 36.87. So likewise, we can find Is value. So I will repeat this one again. I will repeat this. 20 kVA, that is the rated power, rated apparent power. Apparent power means Vs multiplied by Is. So if I divide apparent power by the voltage of the load, which is given as 480 volts, we are getting 20 kVA divided by 480 volts, which is equal to 41.67 amperes. That is the magnitude of secondary current. Okay, so further in the question, you were told that the load is lagging, and the power factor is 0.8. So power factor 0.8 means the angle value referred to 0.8 is cos inverse 0.8. It is equal to 36.87, and since it is lagging, it is minus 36.87. Therefore, the angle of the current is minus 36.87. Therefore, Is we can find as 41.67 angle minus 36.87. Right. So when we have the angle, right, we can find what is ISOA. ISOA is Is value divided by our turns ratio, which is 16.67. So we are getting ISOA, which is equal to Is dash 2.5 angle minus 36.87. Right. So therefore, what is if we apply Kirchhoff's voltage law, Vp, or the primary voltage, that is equal to Vs dash. What is Vs dash? Vs dash is AVs, right? AVs. So if you can remember, Vs is 480 volts, right? 480 volts, and the angle is 0. Vs is 480 volts, angle is 0. So when we multiply it by 16.67, we are getting it as 8000 angle 0. So Vs dash is AVs plus Req plus JXEQ multiplied by Is dash. Is dash is Is over A, with the value that we have previously found. So Vs dash, right? Vs dash is A into Vs. A is equal to 16.67. Vs is equal to 480 angle minus angle is 0, so therefore it will be 8000 angle 0 volts. Vs dash, which is AVs, right? Req and JXEQ we can find as we have learned, as you have learned previously, 45.9 plus J 61.7, right? Then multiplied by 2.5 angle minus 36.87. So it will result Vp as 81.85 angle 0.38. So what you have to understand in here is when we are considering this Kirchhoff's voltage law equation, right? We have considered, or we have moved our excitation branch to the uh, to the close close to the input side. That means Is dash means Is over A. We have taken, that is the current going through Rp and Rp value and x value, xs value, xp value as well. Can you understand? So in here, REQ and XEQ, it is found as the same method that we have used previously, right? So therefore REQ is 45.9 and XEQ is 61.7. So REQ in here is actually RP plus A squared RS. XEQ is XP plus A squared XS, right? So therefore that is the method that we are. So when we are multiplying by IS over A, we are not multiplying. We are we will multiply REQ and JXEQ, right? Not according to the figure. You may see that we have to multiply only RS A squared RS and A squared XS, but it is not. We are multiplying R R RP plus A squared RS and plus J in brackets XP plus A squared XS. So VP we are getting as 8185, angle is 0.38 volts. So like we have referred the voltage regulation, that is equal to no load voltage minus full load voltage divided by full load voltage. So full load voltage is AVS, which is 8000. No load voltage is when there is no load, it will be equal to primary voltage 8185, and the voltage regulation, that is equal to 2.31 percentage. Okay. Then the next thing is we were asked to calculate the transformer efficiency, right? Transformer efficiency, in order to calculate the transformer efficiency, we have to calculate input power and the output power. So what is the input, what is the output power? Output apparent power, it was given to us as 20 kVA. So 20 kVA multiplied by the power factor 0.8, we are getting the output power, which is equal to 16 kilowatts, right? Then here you can see PCU. PCU means the copper losses. Copper losses means the losses by the resistances. So we have only two resistances. One is RP and the other one is A squared RS, right? A squared RS. So copper losses we can calculate by multiplying IS over A squared into REQ. REQ is equal to RP plus A squared RS, right, which is equal to 45.9. IS over A or IS dash, that is equal to 2.5. So 2.5 is squared into 45.9, that is equal to 287 volts, right? So RP and RS, they are used in the figure in order to represent these copper losses. PCU means copper losses, right? Then PCO means it is the core losses. Core losses means when we have a transformer, you may have learned there's a core, right? So in order to represent the core losses, we are using RC, right? RC is 250 kilo ohms, right? So and it is in parallel with VS dash, right? VS dash means it is actually VP, okay? VP. It is in parallel with VP. VP is so you can see in the figure, it is 8185 squared. So divide by 25 kilo ohms, you are getting as 268 volts, right? So if we add P copper losses and P core losses to P out, that means P out plus P copper plus P core, that is equal to input power, right? Because first we have the input power, then there will be something will be lost for the copper losses and something will be lost for the core losses, then we have the output, right? So since the power cannot be destroyed, P out, in is equal to P out plus P copper plus P core. So therefore efficiency, that is equal to P out over P in, which will be equal to 96.6%. This is our next question. So this one is given like this, right? So we were given open circuit test and short circuit test data, right? And we were asked to find the equivalent circuit of the transformer, right? So if we recall what we have learned in previously, right? The open circuit test means we will open circuit the load. When we open circuit the load, there won't be current going through the load. That means the total current will be going through RC and XM, which is the excitation branch. So therefore we can uh, we can find RC and XM using open circuit test data. Right? VOC is the open circuit voltage, and that voltage will be applied. That voltage will be the same voltage to RC and XM. IOC means um, uh, short open circuit current, which will be the current going through RC and XM or the through excitation branch. Right? POC means the open circuit power. So power is measured as well. Then if we consider the short circuit test, in short circuit test what we are doing is VSC is actually, that is the input power that we are supplying after we short circuit the output. So when we short circuit the output, uh, there won't be any uh, voltage in there, right? Because voltage will be zero, and compared to the current going through the excitation branch, the current going through the REQ and XEQ is very large, right? So therefore we can find the REQ resistance and XEQ value, right? Then in our question, like you were given BSc 19.1 volts, that is the short circuit voltage, ISC, which is short circuit current, then PSC, which is the power when we are doing the short circuit test, right? So our first task is the finding the equivalent circuit referred to the low voltage side. So what is the low voltage side? So first we can refer, it is given in the first line, right? 1000 volt amperes. What is 1000 volt amperes? 1000 volt amperes means that is the rated power, rated apparent power, right? Rated apparent power, output voltage multiplied by output current, 1000 volt amperes. 230 to 30 150 volts means 230 means 230 and 115, that is given us in order to find the turns ratio. Again, therefore A is equal to 230 divided by 115. Okay, so our next question is find the transformer's voltage regulation at rated conditions and 0.8 power factor lagging, 1 power unity power factor, 0.8 power factor leading, right? Then you are asked to determine the transformer efficiency. So here when we are writing the open circuit test, right? In open circuit test I told you that we can find RC and XM value, right? So YEX, that is the admittance. Admittance means 1 over ZC, right? So if you can remember the excitation branch, it will have it will have uh, it will have RC and XM in parallel. So therefore GC, right? GC, that is equal to 1 over RC. Right? GC is 1 over RC. BM, that is equal to 1 over XN. Therefore, the excitation branch admittance, the magnitude, right? That is equal to so impedance is equal to voltage divided by current, admittance is equal to current divided by voltage, right? So open circuit current is given as 0.45 amperes, and voltage is given as 230 volts. So current divided by voltage, we are getting the magnitude of the admittance, which is 0.001957. Okay, so now we know the admittance magnitude, right? Then, then, so as you all know, power is P is equal to voltage V into I into cos theta. So therefore, P is equal to V into I into cos theta. So cos theta is equal to P divided by V into I. So theta is equal to cos inverse of P divided by V into I, right? So therefore, P value is given POC, which is 30 watts, VOC is 230 volts, IOC is 0.45 amperes, right? Therefore, when we are taking cos inverse of this thing, we are getting the angle theta as 73.15, right? What is this theta? Theta is the angle between voltage and current, right? So therefore we can find what is YEX, YEX, since since uh, since the magnitude we know, which is 0.001957, and the angle is minus the 73.15, right? So when we are writing this one in the rectangular form, it will be written as 0.000567 minus j 0.001873, right? So 0.000567, that is referred to GC. GC is actually, it is 1 over RC. Therefore, RC is equal to 1 over GC, right? Which is equal to 1763 ohms, right? Then BM is referred to 0.001873. BM is equal to 1 over XM. Therefore, XM is equal to 534 ohms. Okay. Found RC value and XM value using open circuit test. Now we need to find REQ value and XEQ value, right? So REQ and XEQ, we can write it as that is equal to ZDQ. ZDQ is equal to REQ plus JXEQ, right? So in short circuit test also we were given the voltage and the current, right? So if we divide, so V short circuit, if we divide it by V I open, I short circuit, right? I short circuit, which is 19.1 divided by 8.7, we are getting the magnitude of the impedance, which consists with REQ and XEQ. So this is equal to 2.2 ohms. So this is, so remember, this is the magnitude of the impedance. Then we have to find the angle. Angle means the angle between voltage and current, right? The current and voltage values that we have used in the previous line, which is 19.1 and 8.7, right? So when we have impedance, that impedance will introduce angle between voltage and current. So angle between voltage and current is same as the angle of the impedance. So again, power P is equal to V into I into cos theta, right? So cos theta is equal to P divided by V into I. So therefore theta is equal to cos inverse P over V into I, right? So P is P short circuit, that is equal to 42.3 watts, VSC that is equal to 19.1 volts, ISC that is equal to 8.7 amperes. So when we substitute these things, then after we take in the cos inverse, the angle we are getting as 75.3, right? 75.3. So therefore ZDQ, right? ZDQ, that is equal to REQ plus J XEQ, right? So that is equal to 2.2 angle 75.3, and so when we are adding this in the form of form of, so remember 2.2 angle 75.3. So angle is in here, the impedance angle is positive, right? Because when we have a when we have inductance, it is R plus J omega plus J omega. So impedance will be positive, right? So when we are writing the current will be lagging than the voltage, but impedance the angle is positive, right? So therefore it is 2.2 angle 75.3. So when we are writing it in the rectangle form, it will be 0.558 plus J 2.128 ohms, right? So comparing with the equation, 0.558 is as the Req, then Xeq is 2.128 ohms, right? So we have found our Req value and Xeq value, and also in previous test we have found Rc and Xm value. So then in order to do the next thing, we will convert our circuit to the secondary equivalent, right? So to convert the equivalent circuit to secondary, divide each impedance by the square of the turns ratio, right? So if you can remember, uh, when we are at the secondary side, Req that is equal to Rp over A squared, right? Plus Rs, right? Xeq is Xp over A squared plus Xs, right? Here, 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 you can remember we have found Req, Xeq, Rc and Xm values, right? So when we are converting the Rc value to the um, secondary side, we have to divide that value by A squared. A is equal to 2, right? So not only that, right? All the resistances and reactances we have to divide by A squared, right? Can you understand that? So Req we have found previously, that value divided by A squared, which is equal to 0.140, right? Xeq we have found previously, divide that value by A squared, that will be give us Xeq referred to the second side, which is equal to J 0.532 ohms, right? Rc we have found previously, divided by A squared, which is 2 squared, that then Rc referred to secondary side, that is equal to 441 ohms. Then Xm, divide that value by A squared, we have found Xm value, so therefore Xm referred to S is equal to 134 ohms, right? So now we have Rc over A squared, Xm over A squared, Reqs, Jxeqs, right? And also uh, the volt input side, that will change as AIP and VP over A. Okay. Then to find the required voltage regulation, what we have to do is we will use the previous thing, right? So the rated what is the rated secondary current, right? Rated secondary current. So when we have rated load or load of 115 volts connected to the secondary side, right? Again, this 1000 VA that is the output apparent power, right? Output apparent power, which is equal to Vs multiplied by Is. If we divide it by Vs, which is 115 volts, we are getting Is. Is is 8.7. The Is is just the magnitude of the current, right? And we know when in first one, right? In first one, it says 0.8 power factor lagging. That means the angle of Is is minus 36.87. So cos inverse 0.8 is equal to 36.87, since it is lagging, minus 36.87. So therefore Is will be 8.7 angle minus 36.87, right? Vs, what is Vs? Vs is 115 and it is the reference, so angle is 0. So what is ZDQ? ZDQ is the addition of REQ referred to secondary side plus um, JXEQ referred to secondary side. So we have found them previously. So after when we are applying uh, uh, our Kirchhoff's voltage law, right, we are getting VP over A, right? VP dash means VP over A equal to 118.8 angle 1.4, right? Then finding the voltage regulation again, when voltage regulation is equal to no load voltage minus full load voltage divided by full load voltage, right? So when we don't have a load, when the current of IS is equal to 0, and IS is equal to 0, the output voltage will be equal to VP over A or VP dash, which is 118.8 in magnitude, right? Minus 115. 115 means the VS voltage when we have a load, which we call as a full load voltage. So 118.8 minus 115 divided by 115 into 100%, that is equal to 3.3%. Right? One, the only thing change in here is also the um, angle of IS. When we have power factor of unity, that means there's no phase difference between voltage and current. Therefore, voltage angle is 0. Voltage means Vs of Vs, angle of Vs is equal to 0. Therefore, angle of Is is also equal to 0. So therefore, again you are getting it as we are getting 8.7 angle 0 as IS, right? Then VP dash means VP over A, that is equal to 116.3 angle 2.28. Then again voltage regulation, which is equal to uh, no load voltage minus full load voltage divided by full load voltage, right? So no load voltage, that is equal to VP dash, which is VP over A, 116.3 for this case, minus 115 divided by 115. So voltage regulation will be 1.1%, right? Then 0.8 power factor leading. 0.8 power factor leading is cosine of 0.8 is 36.87. When it is leading means the current is leading. Current leading means the angle in here also, only thing that is changing is the angle of IS, that will change to plus 36.87. So IS angle will be plus 36.87. So when we substitute those things to the equation, we are again getting VP dash. VP dash is VP over A, 113.3 angle 2.24. Then voltage regulation also you can find as we have done previously. So here VP over A or VP dash, that is equal to 113.3 minus 115. 115 is the full load voltage or the voltage when we have a load, then divide by 115 into 100%. Here you can see it is negative, minus 1.5% when we are finding it as a percent. Then again, in order to find the efficiency, we need to find output power and input power, right? So output power, Vs into Is into cos theta. What is Vs into Is? Here Vs into Is is the value that we were given at the beginning. What is the value that we were given in the beginning? So it is the rated value, right? So rated value is 1000 volt ampere, right? So Vs into Is is actually 1000 into 0.8, right? Since it is differing when we have to find this when 0.8 power factor lagging. So 1000 into 0.8, that is equal to 800 watts. That is the output power, right? Then the copper and copper losses. So as I have told you, copper losses are represented by the uh, series resistance. Then core losses are represented by the shunt or the excitation branch RC. So according to our model, copper losses, that is equal to IS squared into REQ, referred to the secondary side. And so when we substitute it with those values, copper losses is equal to 10.6 watts, right? Core losses, that is equal to VP over A squared divided by RC, because the voltage existing through RC is VP over A, right? So which is 118.8 volts. We have found this value previously. Divided by 441, right, which is equal to 32 watts, right? 32 watts. So adding P copper and P core value to output power, we can find the input power, because input power is wasted to copper losses and core losses, and the rest is given as the output, right? So therefore input power is equal to P out plus P copper plus P core. So P out, it is 800 watts, and P in is 800 plus 10.6 plus 32, right? And when we get the percentage, we are getting it as 94.9%, right? So likewise, if you want, you can calculate the output power or the efficiency of the transformer for other two conditions as well, right? So power factor 1, that means unity power factor, and power factor 0.8 power factor leading, right? So you can find the efficiencies for that as well, right? So so likewise we can find all the values by given values, right? So when you are doing this tutorial, what you have to do is you have to first draw the models that I have given you, that means which is in the tutorial, right? Then by drawing those values, you can understand uh, how I have applied these equations, right? So and if you have an equation, right, so I have created a discussion session in uh, in um, in StudyNet or in Canvas. You can refer to that, right? So in there you can post your questions, right, and you can ask questions. So likewise.